Hello, everyone, and welcome to the Biophotonics Discovery Podcast. Whether you're a seasoned researcher, a student just starting out, or you just love a good story about how light is used to solve big problems, this podcast is for you. We're making the discoveries in biophotonics accessible one episode at a time. Hello, everyone. My name is Darren Roblyer. I'm a professor at Boston University in biomedical engineering. I'm also the editor-in-chief of Biophotonics Discovery, a new journal by SBIE. As part of outreach for the journal, we're doing a series of interviews with some of the leaders in the biophotonics field. As part of that effort, I'm here today on location at Vanderbilt University with one of my favorite people in the biophotonics community, Anita Mahadevan-Jansen, the Orrin H. Ingram Professor of Biomedical Engineering. Today, we're going to learn more about Anita, her thoughts on research, education, and our community, and then we'll conclude by talking a bit about the journal for which Anita serves as a senior advisor. So, hi, Anita. Thank you for agreeing to do this.
Hi, Darren. Thanks for coming to Vanderbilt. It's been great having you visit. So.
It's been a great visit. All right, so let's start at the beginning. Tell us just a little bit about your early life and where you grew up.
Okay. So I grew up in India, in Mumbai. I was born in another city, Bangalore, but my mother went there to just deliver me, and then we moved to Bombay, is where we lived. I call it Bombay because that's what I grew up calling the city, not Mumbai, except if I spoke Hindi, because Mumbai is the word for the city if you speak in Hindi. I always wanted to go to medical. That was my aspiration in life from the time I can remember, 5, 6. And in India, if you show aptitude in STEM, your options at that time were medicine or engineering. I did not want to be an engineer. I wanted to be a doctor. And so that's what all my early education was focused on. My own interests were focused on. But at that time, we didn't have entrance exams for medical school. It was purely based on your 12th grade scores in physics, chemistry, and biology. And I lost out by 1 point from being able to get admission into medical school. Hated life at that point in time, walked away, not sure what I wanted to do, but I was really good at physics, chemistry, and math. But I still didn't want to go to engineering school. And so while I did take the entrance exam for the famous IITs, the Indian Institute of Technologies, that's really not what I wanted to do. So I decided, okay, I'll get a degree in physics. Apparently I'm really good at it. So let me go get a degree in physics. So that's what I did for my bachelor's degree at the University of Mumbai. I had a mentor at that time who was the department head of physics, Dr. S.B. Patel. He's always Dr. Patel to me, even after I moved on. He kept telling me to call him by his first name, and I just couldn't do it. He was Dr. Patel. He was very encouraging. Once he heard about my interest in medical, applying physics to medicine, he said, you should look at biomedical engineering. He had done a postdoc at Berkeley. And so he was aware of what was possible here. And so he was the one who started getting me on to looking at and doing some research on what that would mean for me. And so in India at that time, your undergraduate degree now for when you do sciences is a 3-year degree. And here you assume an undergraduate degree is 4 years. So I couldn't apply with the 12 plus 3. I needed a 4th year. So I decided to go ahead and get a master's in physics as well. But then I just didn't want to do 1 year. I might as well have the letters after my name. So I finished doing that, then applied around all over the United States, about to 10 or 12 schools that I could afford. I have to remember this pre-computer days. So you hand-typed, your statement of purpose and sent it around. And I was admitted. Showed interest from a variety of different schools, but they all wanted to see my GRE scores at that time. Well, twice in a row, my GRE scores got canceled.
Why?
Cheating. That was all we heard, is that something had been leaked and it was cheating, and so they were going to cancel scores.
They canceled the scores across the board for
everybody. Yeah, they just canceled the scores the first time for everybody. Said, fine, I'll give it again. They canceled again. So it's okay, I'm not doing it here anymore. So I wrote back to all the schools that were interested saying, give me admission, I'll come, you tell me what scores you want, and in the first semester, I'll give you that score.
Okay.
Everybody said, no, sorry, we can't do that. We need the GREs before we can move forward, except the University of Texas at Austin. Baxter Womack was the name of the director of graduate studies at that time. And I still have the letter I wrote him and his response to me that said, come on, and you need to give me a score of 1100 from verbal and quantitative, and we'll let you continue. I did. I gave him 1400. So he had no reason to complain.
You did that in your first semester or
First
before
semester.
you started?
No,
Okay.
first semester. I was not going to take it in India anymore.
Mm-hmm.
After that cancellation, I wanted nothing to do with trying to do it again in India.
Mm-hmm.
So no prep, no studying. October, I still remember, of 1990. I walked in and gave that exam and gave Dr. Womack my scores. So that's what started my PhD here in the United States. And, you come in, you start looking for an advisor. And I'm going to tell you a story that I don't know that my advisor even is aware. We share the advisor,
Right.
so this will be a funny story. So I'm looking around, I go talk to AJ Welch for a research project. And he says, well, I don't really have anything at this point in time, but we have a brand new faculty member down the hall. Why don't you go talk to her? Her name is Dr. Rebecca Richards-Cordova. I said, okay. And, I've done no research. I don't know who this person is. I'm used to a culture where professors are senior, mostly male, faculty, at least at that time. Now we have a lot more diversity, of course. But so I walked into that door and I saw a very young person who looked pretty close to my own age, in shorts and t-shirt, sitting on the floor unpacking boxes.
Okay.
And I looked there and go, is this the professor? And so I knocked on the door, and I guess I had some inkling of social smarts then, because I said, I'm looking for Dr. Rebecca Richards-Cordova, which is a very generic way to ask the question, are you? And she says, yeah, that's me. Come on in, have a seat. I'm like, wow. I just remember just thinking, wow, and we talked. She gave me the opportunity to potentially work in her lab. I was one of the first students, along with another. And she told me in the first semester to do a research paper on cervical cancer. And then I started working with her to develop fluorescence spectroscopy first, and then Raman spectroscopy for cervical precancer detection. And I started by working, she's starting a new collaboration with MD Anderson. So that's what I did, met with some of her first clinical collaborators, and I go, this is it.
Yeah.
This is what I was meant to do.
The translational aspect, is that what?
Right. Applying physics principles to real people. Because when I did my project, I was going to the clinic. I was talking to patients when they was first brought in, making them feel better because they were all nervous about getting a biopsy done, holding their hand almost literally, distracting them while they were going through the exam. But then applying something that didn't exist, my technology that I was trying to research and develop, made me realize, okay, there's a reason I didn't go to medical school. That's what I was meant to do, develop technologies to help populations of people instead of one patient at a time. That was my aptitude. And that's what led to the rest. I can say more, but I can maybe wait to, if you want me to talk about how I got to be a professor too.
Sure, that's great. And then we're going to fast forward to talk about.
Okay. So I finished my PhD in about 1996. I knew I didn't want to be a professor. And I thought I wanted to get into technology transfer industry, but not big startup. I wanted to do some kind of a startup where I took academic technologies and translated it. At least that's the idea I had.
But definitely not a professor.
Definitely not a professor. And the reason was I thought I didn't have the patience. I wouldn't be able to handle being in the classroom, the questions and whatever. So I said, I love ideas. I love developing ideas. So I'll go after that as my career route. But I also knew my husband and partner, Duco Jansen.
Who you met?
Who I met at graduate school and during my PhD. But he always knew he wanted to be a professor. So I told him, okay, you go find your professor position. I've got a PhD. I'll figure out something to do with my life. So while he was looking, I actually decided to go ahead and get pregnant and have a baby.
Okay.
So I was 8 months pregnant when he came to Vanderbilt. And there we were, new city, new baby, new position for him. But when we came to visit for his second interview, I went with him, and the then department chair, Dr. Tom Harris, asked me what I did for my research, and I told him, and he loved it. He said, okay, I love what you do. I want you to bring that to Vanderbilt. So you can start whenever you want after you had the child. I'll give you a pot of money to get started as a research faculty.
Wow.
So this is not something that happens very often.
Yeah.
Okay. It's a rare
This is great.
circumstances that all came together in our favor. I will say Vanderbilt has a history of supporting two spouses who are in the field to help support them. We have lots of faculty couples in Vanderbilt. And so that's what I did. I said, okay, I stayed home for 6 months. I might have stayed home for a lot longer. The less I did, the less I felt like doing, I would say. I really enjoyed being a couch potato. But then both my mother and my mother-in-law both were like, is this why you got a PhD now? Maybe you want to get out of the house. And so found child care for our daughter and started working at Vanderbilt in July of 1997.
Okay.
I've been there since.
Yeah.
Found I really enjoyed the research. I worked really closely with neurosurgery department. That's where my first project ideas came from. And a few months later, I think our department was interested in hiring a second faculty member in biophotonics or biomedical optics. And they had been striving to get a senior faculty member, and that search repeatedly failed for various reasons. And so they decided to switch it to a junior faculty position. And the department chair, Tom Harris, asked me to apply. I said, well, I don't know about this teaching thing. I said, well, why don't you go try? So he told me to go teach a class. I was really terrible at it, let me tell you.
Really?
My course evaluations were really bad.
Okay.
But he's like, hey, you'll learn. It's fine, and I put in my CV in, the idea being, if I get it, great. If not, I'll go back to plan A. And that's what I did. I think there were about 60 applicants at that time, I believe. They still had me come interview and gave me the position. So I said, all right, let's try it. But of course, growing up, you strive for excellence no matter what you do. Whatever you're given a task to do, you try to do the best job you can. So if I was not going to be good at teaching, I went to our Center for Teaching, who at that time had a brand new director. And I said, okay, I got to figure this teaching thing out. So I worked, and it took about 3 to 4 years before I felt comfortable in the classroom. And the really turning point was when I realized I should treat my classroom the way I treat giving any presentation in research. I was always good at that part. Well, let's make teaching into that same process of sharing my knowledge and exciting.
Well, what were you doing that you had to switch? How was it different than that at the beginning?
So I grew up in India where it's very much didactic. Like I'm in front of the board and the students are there. There's no real interaction. It's very much me against, the professor against the students almost.
Yeah.
Not a lot of, the rare professors who were interactive like that Dr. Patel, who brought props to class. He's the one who brought the first laser I ever saw to class in this nuclear physics course, actually. But that's what I was used to. So and very high expectations, very demanding, very pointed questions. This classroom culture and working collaboratively, making your teaching student-centric was not a concept I ever knew. And that's what I learned, how to do that. And my department was part of an engineering research center on enhancing bioengineering education from NSF. Which involved bringing together learning scientists, learning technology, and biomedical engineering to work how to effectively teach biomedical engineering or bioengineering. And I learned a lot from that, really how to take core concepts, apply this learning-centric way of imparting that knowledge, and found that I actually enjoy this. I can do this, And getting a grant was then one of the other things that happened. We all struggle, which I did as well. Took about 3 years before I got my first R01.
Well, that's not bad at all.
I know now. Yeah. At that time, it felt like life and death.
Yeah.
I was going through my first reappointment. 3 years in, you get to your first reappointment. I had no grants, nothing to show for.
Yeah.
Teaching evaluations terrible. No research dollars. Should I really be doing this? But said, okay, you still have another 4 years to help show, So I said, okay, I'll keep at it. And right after I submitted my documentation for reappointment, I got my fundable score for my R01 on brain tumor demarcation with fluorescence. And so, the rest is history, so to speak.
Yeah.
Just kept going there. Love being at Vanderbilt, love doing what I do, and I'm still here.
And you have a lot of really interesting projects now in a number of different areas.
Mhm.
Most everything translational, maybe not
Mhm.
everything, something related
Mhm.
to basic science.
Yep.
But tell me about a project in your lab that you're really excited about right now.
That's a hard question because, as you know, they have a lot of different projects.
Yeah.
The project that I'm most proud of is the translation of near-infrared autofluorescence for parathyroid gland detection,
Yeah, tell us a little bit
which
about that.
has
Yeah.
been successfully translated into patient care.
Mhm.
So I'll start with that one as a successful translation of biophotonics. And then I'll talk about at least maybe one of my more newer projects that I'm trying to figure out how to make into reality. So that one started with a surgical resident who walked to my door, knocked on my door the day after I actually gave a talk on, I don't remember, fluorescence for tumor margin assessment or something. And she said, Dr. Anita Mahadevan-Jansen, I'm not sure, very Southern. Her name is Lisa White, and asked me if I could talk with her. And I said, sure. She was a third-year surgical resident, had been doing endocrine surgery rotation, and thought really impossible to tell the difference between this tiny gland called parathyroid glands compared to everything else. And I knew nothing about the gland, and she told me a little bit about its role in calcium regulation. And I told her, we'd had this conversation, and I was sure at that point somebody else must have done something here,
Yeah.
So I told her, well, why don't you go look in the literature and see what's being done with light? I gave her some keywords: optics, light, spectroscopy, and the parathyroid and thyroid. And she came back with 7 or 8 papers on thyroid cancer detection and 2 papers on parathyroid cancer detection. And that was it. 2 papers on parathyroid. And we looked at it, and both of them one was fluorescence for parathyroid cancer. The other was Raman for parathyroid cancer. And so I said, okay. And remember, what she was interested in was being able to find the gland, regardless of disease. Cancer didn't matter. Whatever, just be able to find the gland, so what I'll call anatomical guidance. So that's
Because it's hard to find, right?
it's tiny.
and-
It's the size of a grain of rice.
Yeah.
It sits behind your thyroid, which usually you have thyroid surgery and those glands are enlarged. You're trying to dig through and find these little things that you want to retain and not accidentally remove or injure while you're removing the thyroid.
Because what happens if you remove them?
That's when they have calcium problems for the rest. They can't regulate the calcium. They've got to stay on calcium supplements for the rest of their life. All kinds of other indications that go with that lack of being able to regulate calcium. And so we said, all right, so let's get some parathyroid and thyroid tissue, go to the lab, and start measuring various techniques and shine light and see what happens. So we did UV visible fluorescence, which is a big part of my lab. Didn't see anything different between thyroid and parathyroid. Looked at diffuse reflectance. Didn't really see much that was different. Didn't do a CT at that time, but said, okay, let's try Raman spectroscopy. And I was doing mostly 785 nanometer excitation Raman. So we took those tissues that happened to be from an animal model and used the probe, our very sensitive, relatively expensive Raman system. And every time we touched the probe on the parathyroid, the signal saturated. And you go, okay, where's the stray light in the room? Dark room, it should not be saturating. That's what this camera is made for. Started putting little tape, black masking tape on all the LEDs in the room, turned the monitor off, still kept saturating. And we had to reduce the integration time by 3 orders of magnitude to be able to get any Raman signal. Still wasn't sure what was going on, measured.
And this is very different than other tissues.
Yeah,
right?
most of the tissues, you can integrate for 3 seconds and you'll get signal. There's a fluorescent background, but there's some ripples, and you background subtract the fluorescence and you extract the Raman signal. But I had to integrate down to 3 milliseconds to get anything at all that wasn't saturated. But still, there seemed to be something different, but I was still convinced there's something odd about doing ex vivo. So let's submit an IRB and just go do in vivo measurements, because we have plenty of projects that use Raman spectroscopy for in vivo, including the cervix for part of my PhD work. So that's what we did. We got the IRB approved, and the same resident went and made measurements on about 5 or 6 patients focused on doing Raman measurements, and then came to our lab meeting and showed what she'd gotten. And I swear, I don't know, I guess I woke up or had an epiphany, and I went, wait, maybe it's real, this saturated signal. What about we get rid of the sensitive Raman camera, just put a standard ocean optic, some kind of fiber-based spectrometer, and let's see what happens. And that's what we did. And she measured 7 more patients with that, and very consistently in all of them, the parathyroid signal was anywhere between 20% and 5 to 7-fold greater than the thyroid, everything else being silent. But exciting at 785 nanometers.
This is autofluorescence.
Autofluorescence, no dyes, no contrast agents, just simple 785 nanometers of light. And so well, is that the right wavelength? Why is there any fluorescence at all? Well, on the one hand, the Raman community is used to having a fluorescence background that we subtract out. The fluorescence community usually believes that the longest known fluorophore is porphyrins, that you excite about 650 and emits about 710, 720. There's not supposed to be anything beyond that, really. Maybe a little bit from melanin out in 900 something, but there's not supposed to be any autofluorescence in biological tissue in that range. And we were seeing signal that peaked at roughly 822 nanometers. Very strange. Could it be luminescence? Could it be whatever else? We thought about everything, but it was very consistent. You excite, you put a long pass filter, and it always had an emission at 822. So it seemed to be fluorescence, and we did some EEM, excitation emission matrices, to see is there a better wavelength, and it seemed like you got the best signal at 785.
You were already there, yeah.
Somehow, coincidentally, because of Raman measurements, we just happened to be the right wavelength. And so that's what we did. We did about 137 patients to show 97% accuracy. As you know, in our world, that's a very rare thing without doing any fancy math. All we were doing was ratioing parathyroid fluorescence to thyroid fluorescence.
No stats, usually doesn't work that way. The thing you're looking for is bright, and everything around it is not bright. It's glowing. Look at me. Look at me.
Exactly. Absolutely. That's exactly how it ended up being. And so, actually, right about at Photonics West, if I want to say 2010 or 11, a small company came forward to license that technology, and then I started working with them to convert it into a device that could be used in patients, and went through. The thing I did different from perhaps many of our colleagues is I strongly believed in the technology, and I wanted to be there to shepherd it all the way through. I didn't want to just give it to them and say, okay, go build it, and I'm ready for the next project. Roshan Shetty is the name of the CEO of what was Anisys, then became AI Biomed. And he didn't know a lot about medical device development and fluorescence spectroscopy. He built nano IR microscope. So he's new optics, but not this. And so he was a fan of working together, and we both agreed, let's work together. And that's what we did all the way through FDA approval and beyond. I intentionally had no stake in the company. I wanted to be able to have the freedom without conflict to develop everything. And so that's what we did. Took it through, worked with their chief, I guess now, then director of engineering, then later on chief technology officer, who did the product development piece. He trained him on understanding fluorescence. In fact, I just went to his house a couple of weekends ago, and he had Lakowicz's Principles of Fluorescence Spectroscopy in his living room. I said, I remember recommending that book, to learn the fundamentals of fluorescence. And that's what we did. We developed it. We tested it in patients. 35 patients is all we needed to test, because 90% power meant 14 patients. Again, when you're doing simple and the signal is so big, you don't need a lot of patients to show.
You're not used to that result from a power analysis.
No, exactly. I don't know how many times we did that analysis, to make sure it was 14. And so went to the FDA and had it approved through the de novo process, because there's no predicate device.
Interesting.
For the technology. I mean, there was no technology for this purpose, or in general for what we were trying to do in anatomic guidance or in endocrine surgery. It got approved in 2018, or cleared, I think is the correct phrase to use, in 2018. And they started making multiple units to get the KOLs in the world, mostly in the United States, to start trying it out. And that was at that time is probably where I made the next, what I now realize, smart decision. Dr. Frederic Triponet is an endocrine surgeon in Geneva, hospital in Geneva.
Okay.
And he had been emailing me in 2018, probably every month, saying he wanted to talk to me about organizing a conference. I didn't know who he was.
Okay.
Oh, I don't know. Somebody's always asking you to organize conferences, and I had ignored it. But he was very persistent. And I had asked my postdoc at that time to go research him. And he said, yeah, he's an endocrine surgeon known for using ICG for looking at parathyroid vascularity. And he happened to call me he had just picked up the phone finally instead of emailing me, and called me while I happened to be in my office. And we started talking. And so we organized a conference. At the first, it was called Fluorescence Conference, Symposium on Parathyroid Fluorescence.
Okay.
This conference brought together, in Geneva, this conference brought together endocrine surgeons who did thyroid parathyroid surgery. And then they talked about using now ICG and autofluorescence and what worked and what didn't work. Very practical use in clinical cases by people not at Vanderbilt, not me. And I learned a lot about, errors that happen if you don't follow through. I had somewhere along the lines, the indications for use didn't have putting the probe in saline and cleaning it between each measurements, because we always put saline in front of the probe to get better index matching, between the fibers and the tissue, but somehow that got lost in the process. And they were just wiping it between measurements.
Yeah.
Guess what? Blood smear.
Yeah.
Not the best thing for it. So we'd end up with random false positives, and we go, no, there's not supposed to be any signal from there. And so now we've educated a lot of people to use saline between measurements. We did find out some certain things do have false positives. Brown fat, for example, has signal, but
That's interesting.
Brown fat tends to occur mostly in kids. This was all developed for adults, but still, some patients can have it. And occasionally lymph nodes will come up positive. That's a whole nother discussion. But people are using it, and it's exciting. And about, not this year, but last year, we had the same conferences ongoing. We now call it the International Society for Innovative Technologies in Endocrine Surgery, or ISITES.
Okay.
We started a society. We started a society, and now it's expanded beyond fluorescence to other technologies for endocrine surgery. The conference still goes on. We had it in Nashville last year. It was in Barcelona just a month ago. But it really brings the surgeon. It's a very unique conference. It's not a give a talk. It's, here's how I used it. Now you give me feedback, ask me questions, back and forth between engineers, scientists, industry, and surgeons. Been very successful, and one of the key surgeons made a statement that made me go, He said, NIRAF is here to stay.
What's NIRAF?
Near infrared autofluorescence. NIRAF is here to stay. And it's not an acronym I would have used. They coined the acronym, so we're going with it here. I'm so used to always saying autofluorescence, right? And so I felt, okay, I did my job. I have done what I've aspired to do, develop a technology using physics principles and applied to medical practice where surgeons are now using it.
Yeah, as part of the standard of care?
They use it for difficult cases.
Okay.
They like using it for difficult cases, mostly. More and more people are starting to use it. It was released. I should add that AI Biomed, which is the company that developed the device, got bought over by Medtronic in 2020, right in the middle of pandemic. So there was a bit of a halt for 2 years because of that. But since they've taken it on, they released it in Europe, in Australia and New Zealand. So people are starting to adopt it. So.
Yeah. That's such an exciting story. I mean, that's what we're here to do, right?
Right.
Change patient care for the better, but it's pretty hard. Now, do we know yet what the autofluorescence signal is?
Unfortunately, we know what it's not.
Okay.
We've eliminated a lot of things, but we haven't been able to When you don't know what you're looking for, it's a real needle in the haystack problem.
Yeah.
So we've eliminated, we know it's present in chief cells. In the parathyroid gland, it's in the cytoplasm of the chief cells, it's in the organelles, pellet part of the chief cells. We think it's inside the secretory granules in the cytoplasm, which is what produces the hormones.
Okay.
But it's not vitamin D, it's not parathyroid hormone, it's not, we don't think it's a protein, think it's a small molecule. So I know everything around it without knowing it's that.
Yeah.
So, but I'm also not a microbiologist or molecular biologist. I work with them to try to figure it out. We talked about doing mass spec analysis, but the problem is if you don't know what category to look for, you just get a long laundry list of things. So it's still in the process, let's just say, what the fluorophore is. But it works, and it works very consistently and doesn't cause harm.
Yep.
Which are sort of the three tenets of what we do.
I love that story also because it involves discovery and translation, right? Two of our favorite things.
Right.
Okay, so you said you had another project.
Yeah, so I mean, I do about a quarter of my work is focused on surgical guidance, various tools. A quarter of my work is focused on developing spectroscopic methods to identify tissue anatomy and physiology and pathology, like disease diagnosis kinds of things, or tracking physiologic change. About a quarter of my work is on infrared neuromodulation, using pulse infrared light to activate the nervous system. And a quarter of my work is focused on developing novel microscopes and making it available for the broad community at large, at no cost. So those are sort of my missions, if you will. But of course, my first love is clinical translation, which a lot of them pretty much follow, except for the microscopy part of it. And so Raman is something I helped develop during my PhD and apply it for biological systems. So I'll use one example because it brings my family and what I do together in a little bit of a strange way. In 1998, I was in Berlin. My daughter was about a year old. Was very prone to ear infections. And Duco called me up to say, yep, one more ear infection at 2:00 in the morning, and we had to go get antibiotics. I happened to be sitting with a bunch of leading infrared spectroscopists who worked in infectious diseases and looking at bacteria. So I said, do you think it would be possible for us to develop a device that we could look into an infant's ear or a kid's ear, identify what bacteria it is, therefore get the antibiotic without having to go and wait at 2:00 in the morning and get the prescription filled? And like, well, I don't know about that. I know if you can get it, we can grow in a petri dish. Maybe, it's worth talking about. And that started a project on developing Raman spectroscopy for acute otitis media detection. Presence of active infection, as well as potentially detecting what bacterial strain it was.
So tell us, if you had that information, how it would change treatment.
So if you knew that it was active infection, you would be able to prescribe. If you knew it was a bacterial infection as opposed to a viral infection, you could prescribe an antibiotic because viral infections wouldn't do anything. You would just let it live its life. And if you knew what bacteria it was, you could be very targeted in treating otitis media instead of providing essentially broad spectrum antibiotics, which then can lead to antibiotic resistance and all kinds of other challenges related with that. And so that was the thought process, because my daughter literally had an ear infection. We gave her antibiotics for 10 days. You waited 3 or 4 days and it was back again. And I would say nonstop for 6 months. She was on antibiotics before she was old enough to get tubes put in. And then it started to get better. In her case, my son had the same issues. But in his case, he still had ear infections even after tubes. So, it's one of the largest, the most frequent reason a kid goes to the pediatrician in the United States. Number one reason, if I remember correctly. And so that was the motivation to develop something like an otoscope, but that had, spectroscopy or some way of detecting. But so we developed that technology. We started to make measurements on different types of bacteria, infection, developed the instrument to do it. But we found that we kind of need, the eardrum is at a slant. If you were to think about your ear, it's actually, it's not directly viewable, it's at a slant, which means the fluid is, if you just put the otoscope, it's sort of down in the bottom. you kind of need to know where the fluid is in order to be able to make measurement from the liquid that's behind your tympanic membrane or the eardrum to tell what's going on. So we decided, we need to add another modality to help us guide where we're going.
Okay.
So about the same time, Steve Beaupart was working on using OCT for otitis media and biofilm development. So we decided to collaborate together and build a Raman OCT device that would one would guide us through, let us know how the state of the tympanic membrane and tell us where the fluid is. And then Raman would give us the active infection, bacterial, presence of bacteria, and then what strain of bacteria. So that's a project to me that brings my love for my kids and wanting to help children and through to applying something that would make a difference. It's not as easy a problem as the parathyroid, a lot more smaller signals, a lot more, the anatomy is tricky, the physiology is tricky, you have a screaming, twisting, turning baby to make measurements for. So we're not there yet in this project. We know we can get signal and tell the presence of active infection or not. With Raman spectroscopy, we know we can identify where we need to go and identify the presence of biofilm with OCT. We've built a device, an otoscope with an umbilical cord, if you will, that can do both. So we are just at the starting phases of making patient measurements with that technology. We have a joint R01 to develop this technology together because you're bringing two experts together to work on this. That was very well received because the likelihood of success hopefully goes higher by bringing two people, bringing together this. So I'm really excited. That's one of the projects. I mean, my other students might get upset for not talking about their project, but this is an example of how I think and how I like to work.
Yeah. And I didn't ask you for your favorite project, just one you're excited about.
Exactly. Exactly.
Okay.
Yes.
Great.
That was a fascinating look into Anita Mahadevan-Jansen's journey, from her time in India all the way through to the incredible translation of near-infrared autofluorescence into clinical practice. Hearing how a challenge in the operating room led to such a successful discovery and change in the standard of care is exactly what this podcast and Biophotonics Discovery, the journal, is all about. Because Anita had so many fantastic insights, we've broken this conversation into two parts. Next week, in part 2, we'll hear about her philosophy on mentoring and what she thinks the biophotonics community needs to improve, her experience as SPIE president, and her role as a senior advisor for the journal Biophotonics Discovery.
If you enjoyed this episode, please subscribe, leave us a review, and share it with your colleagues. Your support helps us shine a light on the latest in biophotonics research. Stay curious, and we'll see you next time.